Okay, so today we're going to talk about moving electricity. Last time we talked about electrostatics, which is basically a big electric charge that is not moving. And we talked about how charge is produced by an imbalance between the number of protons and electrons in an object. We talked a little bit about what it means to be positive. It means you have more protons than electrons, and negative means you have more electrons than protons. So we kind of have all that under our belts. We talked about the ways that you can charge an object, and we talked about Coulomb's law, which basically tells you that if the charges are the same, they're going to push away from each other and repel, and if the charges are the opposite, they are going to attract. We even got into how much charge a proton and an electron have. That's the fundamental charge. And we ended up with calculating the strength of a charge on an object. Today, we're going to talk about what happens when charges move. So, electricity. Electricity is what we call it when charges move, than when they flow through a circuit. Many people describe electricity like water in a river. So the more electrons there are, the stronger the electric current, just like the more water there is, the stronger the current in the river. So you're going to hear that theme throughout the day today. Um, the more electrons you have, the more current there is. There's some symbols that I need to introduce to you today. So the first one is I. I is the symbol for electric current, and the units for electric current are amperes. This is very related to what you've already learned because you know that Coulomb is a measure of charge. You know that seconds are time. So an ampere is measuring how many coulombs of charge go through a wire each second. Just like the current in a river is how much water passes by each second. Here you have a side-by-side drawing of an electric circuit and a water tower. There's a real strong analogy here between electricity and water. So this right here is the symbol for a voltage supply, like a battery, which is basically doing exactly what the pump does in a water tower. So water gets up to the top of a water tower by use of a pump. The pump pushes the water up into the air because then it's got potential energy which allows it to fall. That's exactly what a battery does to the electrons in a circuit. It pumps them up with voltage so that they have the ability to go all the way through the circuit, just like this water goes all the way through the pipes to your home and then back to the source. So the reason this works, water is able to fall through the pipe because it's up in the air and gravity pulls it downward. It has gravitational potential energy. That's exactly what happens over here, except instead of having potential energy due to gravity, you have electric potential energy. So um, the push from the battery forces the electrons to ride along this circuit. A circuit is just another name for a closed loop. So the electrons will go through and come back to the start, get pumped up, and keep going. Just like the pump pushes the water up into the tower, gravity carries it down to your showers, your water faucets, your sinks, and then it gets back to the source. This thing right here we'll talk about in a second, but this is a resistor. So the idea is it can't just flow through nothing, it needs something to guide it. In an electric circuit, what's guiding the electrons is a copper wire or some other type of conducting wire. Just like over here, the water's not just shooting out of the tower, it's flowing through a pipe, and the pipe is what guides it. By slowing it down and guiding it, it gives it some resistance. It slows the flow. Here are some basic symbols that I want you to write down, so I'm going to pause it here for a second while you do that. The basic parts of a simple circuit. This thing on the top is a resistor. It kind of looks like alligator's teeth. It can go either horizontally or vertically. If you put one of those inside of a circle, that's a light bulb, or sometimes you'll have like a pigtail loop of a wire inside of a circle. That's a symbol for a light bulb. When you have a little line parallel to a slightly larger line, that is one cell of a battery. You can have those double stacked, and then it's like you have a double cell battery. And then the last one is a wire. All right, so now we're going to get into some of the equations that sort of govern the rules of a simple circuit. So first of all, the amount of current going by, we talked about this, but it's how much charge goes by each second. So current is I, measured in amperes. Q is the symbol for charge. You saw that in Coulomb's law last time, and we measure charge in coulombs. T is measured in seconds. So if you take the number of coulombs divided by the number of seconds, that will give you the electric charge. That's how strong the electric current. That will give you how strong the electric current is. Well, the rules that govern how many electrons can flow through a circuit have to do with two other things. It has to do with not just current, but also the voltage, which is how much energy each electron has, and then something called resistance, which is kind of like how wide the path is for the electrons to follow. So what is Ohm's law? This is probably the most important law in all of electricity. Electricians have to know Ohm's law. V is voltage, and you know this from looking at battery cells, you know this from looking at the back of any electrical device, including cell phones. It will tell you how much voltage your device battery needs. I, we talked about, is current. R is resistance, and this has to do with how much freedom the electrons have in the circuit. The harder it is for them to flow through a circuit, the more resistance there is. So today we're going to start to look at how Ohm's law affects simple circuits, and we're going to also do some simple math problems and some basic circuit drawings. One thing you should know is that Ohm's law is also often written in terms of R. So if you rearrange this equation, you'd have to divide both sides by I, and that would cancel out on the right, and your new equation would be resistance equals voltage divided by current. Okay, that's it for your notes today.